We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver.
It's one small step for man, one giant leap for mankind.
It is in human nature to be attracted to the unknown. Our species is driven to push our scientific and technical limits to its boundary, which is why the discovery of other planets and life forms beyond our own solar system has been one of our most important challenges yet. With the observable universe being 90 billion light years in diameter, our optical telescopes can only see so far. This necessitated the invention of a new kind of telescope, a telescope which could see the invisible, the radio telescope. But first, some background information. Before we can understand how a radio telescope functions, we must first grasp the concepts of electromagnetic radiation and the electromagnetic spectrum. In essence, the electromagnetic spectrum is the way in which we can see different types of electromagnetic radiation, also known as light. The spectrum measures two out of the four characteristics that make light unique: the frequency and the wavelength, both of which are numerical values. The first of the two values is frequency. That is, how many times the wave repeats itself per second. Here we can see two oscillating waves. If we take the orange wave to be electromagnetic radiation, and the purple wave to be the magnetic component that is perpendicular to it, we can say frequency is how many times the orange wave goes up and down every second. The second value is wavelength. The wavelength is described as the distance between two successive troughs or peaks, and it is represented by the Greek letter gamma. The wavelength is found by putting the frequency to the power of -1. This is called taking the reciprocal. This means that as frequency increases, the wavelength decreases, and vice versa. While frequency is measured in hertz, wavelength is measured in meters. The other notable characteristics of light is that it travels at the speed of light, it has oscillating peaks and troughs, and it has a perpendicular magnetic component. Given this, we can understand how a radio telescope works. There are four main components of a radio telescope: a parabolic dish, an antenna, a receiver and amplifier, and a recorder. Let's start with the shape. The dish's shape must take the form of a parabola. This is because parabolas have the special property of having a focus point, meaning the light that is reflected off the surface of the dish always passes through a singular point. This ties directly into the second main component, the antenna, which detects the light. Because of the parabolic shape, the antenna is positioned at the focus of the telescope. This lets all the light that is reflected from the dish to pass through the antenna. As for the function of the antenna, it simply receives the information about the light. The third component of a radio telescope is the receiver and amplifier. These two instruments work in conjunction. The receiver reads information from the antenna, and the amplifier strengthens the signal. The signal needs to be strengthened as the raw data is too weak to interpret. The final component of a radio telescope is the recorder, which, as you may guess, records the information from the amplifier. Most radio telescopes have digital computer memory to record the radio signal. So, how can we tell the position of stars with a radio telescope? Well, one way is the radial velocity method, which uses a combination of the Doppler effect and redshift. On the previously mentioned electromagnetic spectrum, light that is more red has a longer wavelength. This relates to the Doppler shift, which is the apparent change in a wavelength of a periodic wave relative to a stationary observer. As you can see, when the vehicle approaches the stationary observer, the sound repeats very often. However, when the vehicle passes the stationary observer, the sound is longer and repeats less often. This is the Doppler shift in action. From this animation, we can see that this is because the object in motion is moving in the same direction as the sound, or in our case, the planet is moving in the same direction as the electromagnetic radiation its star is emitting. With this knowledge, we can say that if the electromagnetic radiation is being redshifted, or the wavelength is getting longer, then the planet is moving away from us. And if the light is being blue shifted, or the wavelength is getting shorter, the planet is moving towards us. The Doppler shift assists astronomers in locating stars that have orbiting planets. When a mass orbits a star, there is a push and pull relationship between the celestial bodies. The larger the mass, the stronger the pull. This creates a wobble effect, elegantly named spectral wobble, that makes a star have a circular or elliptical path of motion. This is the radial velocity method. So, what does this have to do with radio telescopes, you may ask? Well, if your radio telescope tracks a periodic shift of spectral wobbles, we know we found a planet in orbit. Radio astronomy has previously helped identify the cosmic microwave background radiation. As well as this, cold clouds of gas found in interstellar space that emit radio waves have helped radio telescopes map out the structure of galaxies. Most importantly, for searching for life outside of our own solar system, radio telescopes help us identify celestial bodies in orbit called exoplanets. Exoplanets are planets that orbit a star outside our own solar system, which are able to identify using the radial velocity method. But why waste resources searching for planets we'll be never able to visit? Well, if we ever plan to find life beyond our own solar system, we'll first need to consider 4 things. Can life based on carbon develop? Is there a presence of liquid water? What would even resemble life if the gravitational pull was different to Earth's? Is the planet in the habitable zone? And whilst we have yet to discover a planet with light that has survived these conditions, radio telescopes allow us to locate newer and unseen planets, only increasing our odds. In fact, our odds of finding life beyond the solar system can be approximated thanks to the Drake equations. This demonstrates the important role of radio telescopes in searching for life beyond our solar system.